Hi everyone. Problem 23 in section 2.2 is one of the more challenging problems that we'll face in this course. So I thought what I'd do is go over the problem in detail via video. The problem states that you must prove that A union B equals A if and only if B is a subset of A. I think the first thing that you want to do when you look at a problem like this is try to visualize it, see if it makes sense to you. So what you've got is you've got A union B equals A. So if I have a Venn diagram and I know that A union B equals A, well, A union B would be if you've got the A circle and the B circle. A union B would be everything that's either in A or is in B. So it would be all the region that's shaded in A and essentially A or B. If A union B equals A, in other words, that set equals only what's in A, then that would mean that, so if A union B equals A, if A is like this, there's A, and B is a subset of A, so B is within A, then A union B, we'll see everything that's in A is in here, everything that's in B is in here, so A union B equals A means that B would have to be a subset of A. So what I'd like to do next is take a look at the statement itself, and this is where it gets a little tricky. The statement says, again, A union B equals A if and only if B is a subset of A. So first thing that we have to apply is a logical equivalence. How do you address if and only if statements? If and only if, so P, statement P if and only if Q is equivalent to two things, that P implies Q and Q implies P. So anytime you want to prove an if and only if statement, you really have two things to do. And I've listed them out down here. Okay, so what we've got to do to prove this statement, we have to prove two things. First of all, if A union B equals A, then B is a subset of A, so that's going in that direction. And then we also have to prove the other direction, because if and only if Q implies P. So if B is a subset of A, I'll do it in a different color. If B is a subset of A, then A union B equals A. So that's going back in this direction. So we've got two things to do. Now here's where it gets even more tricky. The second part of that, if B is a subset of A, then A union B equals A, has another sort of tricky part, and that is we've got to show that one set equals another. Well, here what I want to do is use the set equality definition. Okay, and let me extend this just a little bit so it becomes a little. There we go. Let me move this out, and then you can see it won't be so. Yeah, it's a little bit better. Okay, so set equality says that two sets are equal, okay, if and only if, so A union B equals A, which is what we'd have to prove in part 2, if and only if two things are true. A union B is a subset of A, and A is a subset of A union B. So the second part of part 2 is another two-part proof, and that's why I've labeled them down here. I said from part 2 we really have two other things to do. So from part 2 we've got to do part 2A, show that if B is a subset of A, then A union B is a subset of A. And we also have to show that if B is a subset of A, then A is a subset of A union B. Alright, so to do this proof there are three proofs that have to be completed. Part 1, Part 2A, and Part 2B. Okay, so now let's focus on the first one. Prove that if A union B equals A, then B is a subset of A. All right, so what we have to do is we have to start out with an assumption, and let's do this proof directly. So we want to prove that if A union B equals A, now to show that B is a subset of A, we need to show that if X is in B, then X is in A. All right, so what we do is we would start out with our assumption and our proof, assume that X is, A union B equals A, and X is an element of B. If X is an element of B, then we know that well, you have to show that rather that X is an element of A. If X we can show X is an element of A, then we know that B is a subset of A. All right. So if we have that X is an element of B, we know that A union B equals A. So if X is an element of B, what that implies, and I'm going to apply a logical equivalence here, that X is an element of B, or X is an element of A. And that uses a logical equivalence, that P implies P or Q. In other words, if we know P is true, then we know that P or anything we want to say is true. So for example, if today is Sunday, I'm watching a football game while I'm doing this, today is Sunday. If I say today is Sunday, that's a true statement. If I say today is Sunday or today is Monday, that's a true statement because today is Sunday. If I say today is Sunday or I'm in California, that's also a true statement because today is Sunday. I can say, if I know that P is true, I can say P or anything. So I pick something judicious, something prudent. I know that X is in B. I would like to place it in A union B. So if I know X is in B, I know that X is in B or anything, so I say X is in A. Well, so since now we have this idea of commutative property of statements, I'd say since X is in B or X is in A, we know that we can commute those. X is in A or X is in B. Okay, but now we know that since X is in A or X is in B, we know that this is the definition of union, that X is an element in A union B. Oops, sorry. But now X is an element of A union B, but A union B and A are the same set. They're equal. So I'd say since X is an element of A union B, we know that X is an element of A, and that's since A union B equals A. All right. So what have we shown? We've shown that if X is in B, then we know that X is in B or A, which means that X is in A or B, which means, and this would be the definition right here, I didn't write it down, this is by the definition of union. So if X is in A or B, I know X is in the union, A union B. But now, since A union B and A are equal, I know since X is in A union B, it's in A. So if X is in B, then X is in A. So since X is in B implies that X is in A, what we can say is that B is a subset of A. And part 1 is done. You leave that as an open bracket because there are other parts to do. Now, let's take a look at part 2a. Okay, part 2a says, prove that if B is a subset of A, then A union B is a subset of A. All right, so again, just as we did before, what we wanted to do is we want to assume the hypothesis. We'll do this directly, as you do with most set proofs. Assume that B is a subset of A. And, again, to show that A union B is a subset of A, what we want to show is that if X is in A union B, then X is in A. All right. So let's assume X is in B union A and X is an element in A union B. So now if we can show it must be an A, then we know that A union B is a subset of A. All right. So let's look at that. Since X is an A union B, we know that X is in A, or X is an element of B. Whenever you have an or statement, that gives you two cases. You don't know which one's true, but what we're hoping is that both of these cases lead to the statement that X is an element of A. So we'll look at case 1. So by case 1, we know the or statement's true, so that says either X is in A, and case 2 would be X is in B. So if case 1, X is in A, well then we're done, okay? Because what we wanted to show was that X is in A. Okay, so if X is in A, then we can say, then we know that X is an element of A union B implies that X is an element of A, which would say that A union B is a subset of A, and that would be done. So there we'd show that A union B is a subset of A. But we also have case 2. Case 2 says, again, back to this or statement, we know that either X is in A, which is case 1, or X is in B, which is case 2. So case 2, let's assume, let's let X be an element of B. Oh, okay, well, since X is an element of B, let's go back to our original assumption. Okay, since X is an element of B, and remember we assume that B is a subset of A, we know that X is an element of A, and that is by the definition of subset. So again, X is in B. Okay, that implies X is in A. Well, actually, we started out with, we started out with it, X is in A union B, applies X is in A. Okay, because we said case 1, if it's in A, well, we know that it's in A. If it's in B, well, but B is a subset of A, so we know it's in A. So again, we have that X is in A union B implies X is in A. So A union B is a subset of A. So in either case, so either in case 1 or case 2, we can say that A union B is a subset of A. And we're done there. Now, we have one more part to go. I told you this is a long one. Okay, and that is part 2b, which says that prove that if B is a subset of A, then A is a subset of A union B. Actually, this is going to turn out to be the easiest one to do. Again, your assumption, we want to assume that B is a subset of A, and we know that to show A is a subset of A union B, we now got to show that X is in A implies X is in A union B. So we'll assume that X is in A. Okay, this one is nice because it really doesn't use this part of the assumption B is a subset of A at all. Since X is in A, we know that X is in A, or, and again this goes back to the equivalence, that P implies P or Q. Okay, so we can say X is an A or anything. Well, what would we like to say? We'd like to say that here we're trying to get to the fact that X is an A union B. So why don't we just, again, pick something prudent. If X is an A, then X is an A or X is an element of B. Again, we could have said anything there. It doesn't matter. Since X is an A, we know the first part of this OR statement is true, which says we could say anything here. But now, since X is in A or X is in B, we can state that X is an element in A union B, and that's by the definition of set union. Okay, so what have we shown? We've shown that since X is in A implies that X is in A union B, we can say that A is a subset of A union B. One last thing, and so that would be the last part of our proof. So we'd have the box, and it's colored in because it's the last part of our proof. Just one last comment, and this isn't about this problem per se, but about a few other equivalences which are really nice to have. I'll mention these in class, I'm sure. But we've used the fact up here. You can see that P implies P or Q. That's a nice equivalence to have. A few other things that are nice. We know that, and let me do in black, we know that P implies P and P. So in other words, if we know that P is true, then we know we can say that P and P are also true. Let's see. And I think that's probably, so those two are two very nice equivalences to have. They'll come up in problems as we go through the semester.